Hi guys, welcome to chapter number 8. We'll be looking at the rigid and flexible mechanistic models. So we'll start with the flexible pavement mechanistic model. Okay, so mechanistic models are used to mathematically model pavement physics. There are a number of different types of models available today. You can use a dynamic, a viscoelastic model, but for this section we'll present two. So the layered elastic model and the finite element model. We know what a finite element is if you did structural engineering. If you've done dynamic loading or seismic engineering, you know exactly what I'm talking about. You can use finite elements to determine how they'll interact or how they'll respond to earthquakes, how they'll respond to hysteria. But yeah, that would be for obviously people who studied at like University of Auckland or in New Zealand where earthquakes are prone, and in some parts of America where earthquakes are prone. And also like for like I think second year calculus, we also deal with finite element models. You know, those the double integration, triple integration. So those are that's you have a finite element, you're integrating it. I think you also use it in bridge design. But yeah, moving on. Both of these models can easily be run on a personal computer and only require data that can be realistically obtained. So the idea is when you're using these models, you'll be using them in a software. You're not going to be doing hand calculations because that will kill you. Most definitely that will kill you. Okay, so let's start with the layered elastic model. Okay, so a layered elastic model can compute stress, strain, and deflections at any point in the pavement structure, right? Resulting from the application of a surface load, right? Layered elastic models assume that each of the pavement structure layer is homogeneous, isotropic, and linearly elastic. In other words, it's the same everywhere. Like they assume that everywhere it's exactly the same, right? So then the origin of the layered elastic model is from Busnik, okay? Yeah, I remember studying that in math, who published, you know, his classic work in 1885, right? So today the charts are widely used in soil mechanics and in foundation design. Yeah, I remember seeing in GI, I remember seeing that also in some class, but that's fine. And this section, you know, covers the basic assumptions, inputs and outputs from like a typical layered elastic model. Okay. Okay, so the assumptions we have, the layered elastic approach works within a relatively simple mathematical model and thus requires some basic assumptions. These assumptions are the pavement layer extends infinitely in the horizontal direction. The bottom layers, usually the subgrade, extends infinitely downwards, which is true because it extends, well, in this case, we would say infinitely downwards to the Earth's core, right? Materials are not stressed beyond their elastic range, which would also assume because we're saying it's a flexible pavement, right? A layered elastic model, these are the inputs. So a layered elastic model requires a minimum number of inputs to adequately characterize the pavement structure and its response to loading. These inputs are the material properties for each layer. So that would be the modulus of elasticity, the Poisson ratio, the pavement layer thickness, and the loading conditions, right? So magnitude, V, the total force P applied to the pavement surface, geometry, right? Which is usually specified as being a circle given a radius R or A, and the radius is computed knowing the contact pressure of the load P and the magnitude of the load P. Although most actual loads more closely represent an ellipse, but we just use it as a circle, right? Because the differences in geometry, we assume that they're negligible at a very shallow depth. So we just use a circle instead of an ellipsoid or an ellipse, okay? So repetitions, of course, always. So multiple loads on the pavement surface can be accommodated by summing the effects of individual loads. This can be done because we're assuming that the material is not being stressed beyond their elastic range, okay? So these are very important assumptions when using this model. Okay, so moving on. It shows how these inputs relate to the layer elastic model of the pavement. So you can see in this figure, this is, you can see here it's a distributed load and how it's acting. So this is on the surface, on the base, and on the subgrade. So on the subgrade is infinite, then on the other base we're saying there's a certain height, our H2, and then our H1. So this is how the layered elastic inputs, these are the layered elastic inputs that we need. These are the parameters that we use to find our results or to get a solution using the mechanistic model. Okay, moving on. So the outputs we get, so the outputs of the layer elastic model are the stress, strain, and deflection of the pavement, right? So then when we can know what the stress is, the strain is going to be the deflection, we can know how our pavement is going to perform over time, right? So the stress, this is intensity of, the internal distributed force experienced in the pavement structure at various points. Obviously, stress is measured in newtons per square meter, kilonewtons per square meter, or you could, it's pressure or PSI. That's fine. Strain is usually measured in millimeters per millimeter or inch per inch. And we all know that the strength is the unit displacement due to stress, and it's expressed as a ratio, of course, right? And it will be very normally be expressed as a microstrain, right? Then deflection, that's the linear change. Deflection is expressed in units of length, or nanometers, or micrometers, or inches, or millimeters, right? The use of a layered elastic analysis computer program will allow for one to calculate the theoretical stress, strain, deflection anywhere in a pavement structure. However, there are few critical locations that are often used in the pavement analysis, of course. So yeah, there are obviously certain points where we think that the stress will act on the most, and those are the points that we check for, right? So the critical analysis locations in the pavement structure are the pavement surface, right? The bottom of the hot mixed asphalt layer, the top of the intermediate layer, the base or the subbase, and the top of the subgrade, right? So deflection, here we check horizontal tensile strain, there we check vertical compressive strain, and there we also check vertical compressive strain. So reason for use, used to impose load restrictions during spring, thaw, and overlay design. So we check the pavement surface so that we know what load restriction. So if you have a very heavy truck, there are some roads where you're not allowed to travel because we know for sure you're going to cause rutting. You're going to most definitely cause rutting. You're going to cause, or you might actually cause failure, right? So bottom of the HMA layer used to predict fatigue failure, like I was saying, right? Then top of intermediate layer, you used to predict rutting failure in the base, or exactly, you see, most definitely. Then top of subgrade, you used to predict rutting, because rutting will happen if there's a very heavy load at the base. It will just give in, most definitely. Anyhow, moving on. So this is what it looks like. So this is the critical analysis of the locations of the pavement. Okay. So here at the surface of the surface course, here at the bottom of the HM, here at the top of the intermediate layer, and here at the top of the subbase, as outlined as 1, 2, 3, 4. Right. So this is the tire. Excuse my shorty drawing, but yeah, this is just to show you guys exactly what I'm talking about. Be able to visualize it. Anyhow, let's move on. So now we move into the finite element method. So the finite element method is the one that's typically used. Most softwares the softwares that I'll discuss and the softwares that I'll touch on use the finite element method, and this is the one that we commonly use, the one we use for structural engineering. It's the one widely used for engineering problems. Okay. So the finite element method is a numerical analysis technique for obtaining approximate solutions to a wide variety of engineering problems, like I just said. Although originally developed to study stress in complex airframe structures, like I said, we typically use it in structures, it has since been extended or applied for a broad field of continuum mechanics, right? In a continuum problem, e.g., one that involves a continuous surface or volume, the variable of interest generally poses the infinitely many values because they are functions of each generic point in the continuum. For example, the stress in a particular element of a pavement cannot be solved with one simple equation because the function that describes its stresses are particular to the specific location. However, the finite element method can be used to divide a continuum, right? E.g., like the pavement volume, right, into a number of small discrete volumes, right, in order to obtain an approximate numeric solution for each individual volume rather than an exact closed form solution for the whole pavement volume. So the idea is you're chopping it into little blocks, so finite elements. So you're chopping into little elements, and then you're trying to find how those elements will react in a sense. So 50 years ago, the computations evolved in doing this way incredibly tedious, but today computers can, like I was saying, if you try and do it by hand, it's gonna be a mammoth task. This is not enjoyable. You'll most probably take days trying to do it, and I don't think it's worth it. So rather, just use the softwares, and you're also most probably going to make mistakes because of the repetitive and the iterative process. So rather, just use the softwares that are accepted internationally, and use those softwares and just go through it like that. That would be my advice. That's my 2 cents in that case. Okay, so let's move on. So here's an example of what the finite element looks like. So you can see here there's a crack, here's the tire patch load, right? And here's the slip interface. So yeah, you need a slip interface when you're designing. Yeah, you'll have a slip interface, right? So here is for Everflex 3D drawing adapted from 2001. The drawing shows the discrete element, wheels, loads, tire patches. It just shows exactly what we'll be looking for, and then the dense liquid foundation. Okay. So this is typically what a finite element method would look like if we were to. So you can see all those finite elements, you know, everything, how it meshes in together. Yeah. Anyway, let's move on. So the assumptions, okay? So for the finite element approach works with a more complex mathematical model than the layered elastic approach, so it makes fewer assumptions, which is true. Generally, the finite element must assume some constraining values at the boundaries or the regions of interest. For instance, the computer problem developed by Hongyu Wu and George Turkia at the University of Washington, called Everflex, uses a 6-node foundation element to make the Winker foundation, right? This program also uses free boundaries on the 4 sides of the flexible pavement model. Additionally, the choice of element geometry, size, and shape, as well as interpolation functions, will influence the overall model performance, right? So input, right? The typical finite element method approach involves the following 7 steps, okay? A discrete continuum, right? Select interpolation functions, right? These are nodes that are assigned to each element, and then a function is chosen to interpolate the variation of the variable over the discrete element, right? Find the element properties. You assemble the element properties to obtain the system equation, right? Then you combine the matrix equation expressing the behavior of the element from the matrix and the equations expressing the behavior for the entire system. Then you impose boundary conditions. Then you solve the system equation. Then you can make additional computations if you desire. So that's how we go through it. Okay, let's move on. So the outputs you'll get. So the outputs for the finite element analysis are the same for the layer. You get your stress, your strain, and your deflection. In addition, the finite element method allows for extremely powerful graphical displays of the values. Okay. So this is what you're seeing here, how it will interact. So you can see here from this figure 9, this is the strain diagram, this is the surface strain, this is the figure section view of the strain diagram. If you use Procon, you remember that this is what the stress strain diagrams also look for a slab. They're color coded like that, and they'll tell you exactly what value of stress or strain you're going through depending on the color code. So yeah, it reminds me of Procon. And also a sample load profile to show you a graph for the load profile. So now you know if you add this load, obviously if the graph is skewed like this, you know that there's going to be ratcheting of the subgrade. So very, very good. Here it tells you maximum principal strain and the maximum force. It can, you know, everything is just there for you to know exactly what you're doing, and you can know whether your design works or not. So yeah, very important. And it's also good to be able to visualize this. Visualizing the design also helps because you can really see what you're working on. So yeah, this is just a typical example of what using a finite element analysis software would look like. Okay, so let's move on. So now let's look at the rigid mechanistic model. Okay, so for the rigid mechanistic model, because here we're talking about the flexible, now we're looking at the rigid. So the rigid mechanistic model, same thing. So we also used a layered elastic model. We already talked about that. We won't touch on that, so let's move on. For the finite analysis, it's exactly the same what we were talking about, exactly. exactly the same. Okay, so however, it's a bit different because here the U.S. Army Corps is also is also involved in designing or in the finite element method. So the U.S. Army Corps have their own software, I believe. So feel free to look at that. They're the same guys who created HackRAS and HackHMS. They really know what they're doing in terms of the engineering space. That's a really good place to also get design aids and material for designs. Even also with river engineering, they know what they're doing. If you're designing a rock revetment or things like that, look at their design methodology. It's solid, and I've used it myself for a design, and that project has already been constructed, and the rock revetment is holding up very well. It's at a bridge in Tairafiti in New Zealand called I think it's called Waikaimoko. I'm not sure. I hope I'm not botching the name, but yeah. So here is a sample of the deflection display shown on discrete region, you see. So this is what it looks like if you're dealing with a rigid pavement. You see, this is what it would look like if you're dealing with a rigid pavement and you have a point load there. This is the visualization. You can actually get to see what you're trying to do, how the force will act and how the material will respond. Which looks like amazing. This is visually stunning. You can get to see exactly what you're doing, and you start to understand what's happening with the design. Okay, so let's move on from that. So the assumptions you would have for the finite element approach, right? You work with a more complex mathematical model, layered elastic approach. It makes your assumptions. So generally, if you're using the finite element method, you must assume constraints like we just talked about, and also geometry and interpolating functions. So the input, so it's going to be it's exactly the same as previously before. So this is the input for using ever FE. You know, it looks really nice. You've got your geometry, your dolls, your material, your loading, your meshing, your aggregates, your deflection, your slab layers, you know what, X and Y. It's kind of reminding me of Procon. So if you guys want me to take you through a tutorial of how to use this, just drop a comment, happily do that. So this is just the interface that you'll use, and then so let's move on to what the outputs will look like. Okay, so the outputs for the finite element method of analysis for a rigid pavement. So you're gonna have stress, strain, and your deflection, and this is what it'll kind of look like. So these are your axles, and you're saying that this is where your joint is or your crack is, and then you can see how it will respond from this slab to this slab. You can see this is where your crack is. So you can see the surface strain, and it's the same color coded depending on the amount of strain. So it looks really nice. The visualization is amazing, and you can see exactly what you're doing. So yeah, the screenshot thumbnail was from Eva FE. Like I said, Eva FE is a project developed by the University of Washington and expanded to the University of Maine. The project is supported by the Washington State Department of Transport, and additional supported by, like I said, it's supported by the U.S. Army Corps, and these guys are really good. So I'm just reaffirming what I told you guys about. So most probably, like as I'm going through the course, I'll say some things that I wrote before because I'm seeing them there, but you know, we can always come back to it. So yeah, this is most definitely very good software. You guys can check it out. So yeah, I think this is all for chapter 8. I'll see you guys in the next chapter.